one area of probability that is really valuable and important has to do with Bayes' theorem, which I've stated here and which we'll talk a little bit more about in terms of what all these components mean. So when we're working with probability distributions, this is very often used to compute what we call the posterior. And if we recall, the probability of B given information about A is equal to the probability of A given information about B times the probability of B all over the probability of A. Now, the three pieces that are the most important here are likelihood, prior, and posterior. Evidence sometimes can be obtained, though computing this distribution can be a little bit difficult, as you'll soon see in terms of a little bit of intuition that will wrap around this. But a lot of times we have worked with this formula numerically, right? We haven't really focused on distributions. We've just looked at a single value. So maybe what we know is that the percentage of people and who are qualify as A, so maybe we'll just say who drive an automobile. So if we take a small town and we say, all right, what percentage of people drive an automobile? And maybe what we find out is it's 0.9. Okay, so that's a numerical value. We don't know the underlying distribution of automobile drivers, but this is good enough. And perhaps what we want to know is we have the percentage of people who maybe consider themselves to be busy on a daily basis. I have automobiles and people who are busy. There's probably a connection there. They're probably not independent events. And so we'll probably say, maybe only 80% of people proclaim themselves as being busy. And maybe what we want to know is out of all automobile drivers, what percentage of them are busy? But all we know is the percentage of all people who are automobile drivers in this town, the percentage of all people who are busy, and maybe what we also know is the percentage of all busy people who drive automobiles is 0.7. Okay? All right, so out of all the busy people, out of everybody who says they're busy, 70% drive an automobile. And so what we want to know is we want to know the posterior. So now take everybody who drives a car, and we want to know what percentage of them are busy. Well, using the likelihood, prior, and evidence, we can compute this probability. We can say that we have 0.7 times 0.8 over 0.9. That's 0.56 over 0.9, which is 0.62. It's approximately 0.62. So that means that out of everybody who drives an automobile, 62% of them, or just over half, are actually busy. But of all the people who are busy, 70% drive an automobile. So notice that the group of people who we're talking about here, and forgive my sketching of a car here, but here we have all people who are automobile drivers. We want to know, are they busy or not? Here we're looking at all busy people, and we're asking, do they drive an automobile? That's the question that we have, right? So it all depends on what we know about the group and what we're trying to determine about the group. And so the prior, okay, now looking at this a little bit more generally in terms of Bayesian statistics, where we always consider evidence, and when we take that evidence, we can update our posterior probability. So the prior is a probability that we know before we even see the data, or something we assume about the probability. Now, this is going to come in the form of distributions rather than just the numerical values, just the specific cases. Here there's distributions associated with automobile drivers and busy people, and maybe there's a variance and a mean and all that stuff. But now we're really going to focus on this being wrapped around distributions rather than specific case values. So the prior is just something that we know before we see the data. Likelihood is the likelihood of having observed the data given the prior, right? So it's like, how likely is it that we should have seen this given the prior information, given what we knew before we even saw the data. The evidence is the probability of having observed what we did out of all possible outcomes. Now, this is a very vague and difficult thing to come by a lot of times, and that's why we're only going to focus on the posterior, likelihood, and prior. And the posterior is a probability we see after having observed the data. Okay, so let's put this into context, and really we're going to focus on the intuition here, because the mathematics can quickly get cumbersome, and we just want to understand what are we doing with this. So suppose we have a coin whose fairness we are not certain about yet. We're trying to figure out whether this is a fair coin or not. So we don't know if it maybe favors heads or maybe it favors tails. Maybe it's perfectly fair, 50-50. So what do? Well, to assess this, we collect some data by tossing the coin, and what we want to do is we want to estimate what we're going to call theta. And that's going to be the probability that the coin lands on heads. So typically, what we have observed in the past is that theta is equal to 0.5 for a fair coin. Right? If that coin was fair, we would expect theta to be 0.5. But maybe we don't know anything about this coin. We just heard that it's questionable. And so what do? Well, if you look at what we have here, this is really just replacing A and B with data and or theta. Okay, so let's talk about what these components mean. So this probability of theta, this is some distribution, some assumed distribution theta. Okay, so now it's not just a numerical value specific to the exact data that we collected, but it's going to be more kind of what we know coming into the problem. All right, so here's what we might imagine. One way to approach this would be to say, well, of course, theta, the probability that this coin lands on head, we know that it has to be somewhere between 0 and 1. The probability. Now, as far as the density, what the density should look like for any given theta, because we have no idea whether the coin is never going to land on heads or always going to land on heads, 0 or 1 respectively, we may just assume that this is going to be a uniform distribution. So theta is distributed uniformly, okay? So that just means that right now we are allowing the possibility that theta could be anywhere between 0 and 1. We have no predisposition to believe that it is higher or lower. Now, on the standard coin, you might say, well, we typically believe that right around 0.5, that this should be a really high density, and then, you know, the likelihood that it is close to 0 or close to 1 is going to be very low. But again, we're not making any assumptions about the coin because we haven't met it, we haven't worked with it yet. So that's our prior distribution, right? This is our prior distribution, which is based on our current assumptions. Now, what we do ultimately for the posterior is we want to calculate what is the probability density of theta based upon the data that we observed. So after we collect our data, we can say, well, here's where we believe theta actually lies. Right? So after we analyze, we'll come back to the other pieces here, but maybe based on the data that we collect, we now believe that, okay, theta has to be between 0 and 1. And again, on this axis, we have the PDF, probability density function. Maybe what we believe based on this coin is it's a little unfair we believe that it's maybe, 60-70%, and then maybe this is what we find out, that somewhere the mean is around 0.75, and maybe it's a little skewed, okay? Or maybe we find, as we would expect, that the coin it's highly likely that it has a 50% chance on landing heads. Okay, but this is based upon the data that we observed. All right, so what does the likelihood mean in this context? All right, there's the likelihood. Okay, well, this is asking, based upon the theta, or the distribution of theta, based on the assumed theta distribution, based upon, this over here, how likely is it that our data would have occurred? I'll say observed data happened. So that's what we're seeking to answer with the likelihood in this case. As for the denominator, some people will just refer to this as the denominator. This, of course, is the evidence. And what this is asking is, notice that this has no conditions. This is just saying, what's the likelihood that we observed the data that we did out of all the data possible? How likely is the observed data out of all possibilities of data? And what do we mean by data? In terms of the coin toss, we mean, the data could be that we get, out of, maybe we toss the coin 100 times, and maybe the data that we get is that perhaps we get 64 heads. 64 heads. For example, that might be the data that we observe. And maybe on a second try, maybe we get 40 heads. All right, so that's what we mean by data in this context. What is the result of our experiment in coin tossing? This again is difficult often. Get that data, but the good news is that what we're really concerned about is the prior and the likelihood. Now, with all that said, underlying this probability statement, other than the situation where these are all numerical values and we can come up with a computation, we want to now deal with the probability distributions. And so the probability of A given B will have, this means distributed as, it's going to be distributed as something. B is going to be distributed as something. B given A is going to be distributed as something. Maybe it's normal distribution, binomial, lots of options. Now, I'm going to say here as the note, we ignore the evidence. And that might seem like a weird thing to say, but remember, this is called evidence right here. This is your evidence. That's all we mean by evidence in this context. Or marginal distribution of A, P of A, because it doesn't depend upon B. And it therefore is constant with respect to B. So what we mean by B in this case is that the data is irrelevant to our prior association of theta, and it doesn't depend upon theta, right? That was just data that we collected. The only things that depend upon data are that depend on theta are the posterior, the likelihood, and the prior. And we are interested in the distribution of the posterior probability of B given A, and that distribution can be very complicated unless it takes on a similar shape as the prior. So the posterior, if it's the same kind of distribution as the prior, the solution quickly becomes analytic. And so we're going to define something here. We're going to define a prior to be conjugate for the likelihood function if the posterior is of the same form or type, the same distribution as the prior. So maybe your prior is distributed as normal 0, 1, mean and variance. and maybe your posterior, you find, is distributed normal to 4.6, right? So they are of the same type because they're both normally distributed. We'll take a look at an example and work through how we could actually come up with the posterior in the situation where the prior is conjugate to the posterior.